Hi, good evening, everyone. It's good to see so many of you. So I'd like to at least get a feel for how many people are at least pretty familiar with Julia and pretty familiar with machine learning. I'm hoping it's most of you, but ooh. Right, okay. So if you're not very familiar with machine learning, I'm afraid quite a bit of this talk will fly over your head. I think when Anthony gave the talk at JuliaCon a few months back, he gave a bit of an introduction of why you would want to do machine learning in the first place. I'm not going to do that because, yeah, I think if you're interested in this, please look up the slides. They're online. They're available online and available on the README. But I'll assume that that you kind of have some basic machine learning knowledge. Okay, so the talk will be in more or less 3 parts. One short part, which is the vision or the motivation. Why did we even bother starting this? And then why should you be excited or interested in the project? Then I'll talk about the MLJ Universe. So that's the repositories, where the code is, what the different bits do and why. And then the last thing is, where are we going? And potentially, how can you help us get there if you want to chip in? So the vision, the key vision is that MLJ is designed for composability. So if you're new to machine learning, this might come as a surprise. If you're not, it should be pretty, you should be aware that composing models is usually a good idea in machine learning. If you've ever played, or done a competition on Kaggle, usually models that win are extremely sophisticated models that pile on sequences of many different models and potentially do multiple layers of meta models. And actually, neural nets are just a very specific case of a composed model, right? So that potentially, if one of your question coming here was, why should I bother with this when there is sklearn? I think that's maybe the answer to that question. So sklearn is very good, offers a lot of models. By the way, we interface now with most of them, so you can pretty much use sklearn from MLJ. But composability of things is a little bit clunky. It's something that kind of was added afterwards. So sklearn it's a little bit more of a library of models than really a toolbox that allows you to compose things. Actually, MLJ is takes quite a bit of its the inspiration for its design from MLR, whence the name also. And again, there are differences, but the idea is that try to build from the ground up, trying to have a design that's very strongly towards composability, testing, etc. And then the kind of things that composability allow for is reproducibility. So it makes it easier to specify fairly sophisticated models and then export it as a new model by itself. So once you've created a box with a bunch of operations and you're happy with it, you can export it as a new model. You can train it as such. So it makes training and testing a fair bit easier. And also, and that's part of the vision, the hope is that once you've defined a graph of your operations of what your full model stack should do, then you can exploit this and benefit from Julia's parallelism, from also Julia's ability to deal with different architectures, so not only deal with CPUs, but also deal with GPUs fairly easily. So we're not quite there yet, but that's part of the vision. Okay, so another important part is to enable and benefit from interoperability. So Julia makes it fairly easy to write generic code, meaning that you can write code which will work on types that are not defined yet, for instance. So this makes it very, if you're completely new to the Julia world, that's I would say one of the most interesting feature of Julia, is that you can compose packages which were designed completely independently, and then all of a sudden they work and they make something better, just because of this sort of genericity of how the code is written. And so, for instance, in the case of MLJ, the models are agnostic to the data providers. So we didn't really have to specify anything to do that, but we can already deal with data from data frames, from JuliaDB, from MySQL, actually from a whole load of tabular data. So I mentioned this just earlier. There's also the hope that, Julia makes it fairly easy to write code which works on a CPU, but then can be, with few modifications, can just work on a GPU or on even other architectures. And again, we hope to take advantage of this. Right, and then finally, there is a lot of work in the sort of automatic differentiation from parts of the Julia community. Again, we could benefit from this. So maybe a thing that, if you're new to automatic differentiation, one thing that, let me backtrack a bit. So if you take a library like scikit-learn, a lot of the code is written in Python, and some of significant parts of the computationally intensive bits are written in C++ and are hidden away from you, or in NumPy or whatever. This makes automatic differentiation of like a complicated function more difficult, because you have to deal with several layers of things, right? Whereas if you write everything in Julia, well, you only have the Julia layer to handle. So potentially Julia is very, it could really benefit from automatic differentiation, and it's also reasonably easy to do in Julia. So there is a lot of effort going there, partly to support the neural nets. So there is the Flux library and KNet library. Both of those have their own automatic differentiation tools. And I think, you've got efforts like Zygote that you might have heard of, which is again a source, well, it's one of the automatic differentiation library. And there is hope that that would become like really a sort of go-to tool for that kind of stuff. And again, in MLJ, if we could benefit from this, that would be pretty good, pretty easy. Okay, so finally, there's a bit about helping the community. So part of the reason we started this was that the ML community in Julia is a little bit scattered, and there are several reasons for this. There's a big pull around sort of neural nets. So there are researchers there, and there's a lot of effort into getting state-of-the-art neural net libraries. So for instance, KNet and Flux. And then there is that's my take on it, but there's a bit of tension. Not like interpersonal tension, but there's the people from the stats community. There is a bunch of packages from sort of the statistics ecosystem, and there's the community from ML, and it's not always there is not always a synergy between the two. So the hope is that MLJ could maybe provide an incentive for sort of a unified way of doing things. People don't have to buy into it, but hopefully, if MLJ is to be successful, eventually people will have to buy into it. That's the hope anyway. Okay, so encourage collaboration, and also by allowing people to use several models and chain several different models, what we're hoping for is that the weakness of the ecosystem would be highlighted as well. So for instance, if one of the packages doesn't perform as well, then can we feed that back to the package manager, and can we just make it better, right? So I think ultimately more users further down the line means better program. Right, and then there is the hope that MLJ would provide like a toolbox that people can easily load into their own package. so that, for instance, they would benefit from the get-go from simple tools that would be useful in machine learning anyway. If, for instance, like metrics, things like area under the curve, like this kind of stuff. If you develop a new model, you might not want to rewrite code for it, right? And some of this was already available, by the way, in things like MLBase, so that's unrelated to MLJ. But again, as I said, it's a little bit scattered, and these things don't always interact well. Okay, so now that hopefully you get the idea of why we even started with this, let's go to the MLJ Universe. So, oh yeah, by the way, Avik was very nice, but while it's true that I more or less initiated the idea of supporting an ML library at the ATI that would be written in Julia, most of the work has been done by Anthony thus far, and not by me. I actually joined the project as a dev fairly recently. So Anthony is the core dev, and actually that was, sorry, just a joke. This is Sebastian. There's actually a guy called Sebastian Vollmer, who is a American football player. But yeah. And then there's Franz Kirali, who's not here today. He helped us a lot with the sort of the early design of MLJ, because he's had a fair bit of experience in that. Now he's moved on. I think he works on other projects like SK Time and things. But so his feedback was definitely very valuable to define how like MLJ came to be. Okay, so unfortunately there are many repos in the MLJ universe, and so we need to cover that. There is 7 of them that and counting at the moment. So the key ones that you should care about and add stars to are MLJBase and MLJ. And I'll kind of take them as one unit when I talk about them, because what goes in one and what goes in the other is still a little bit in flux at the moment. But MLJBase, the idea is that it provides whatever is needed for a package dev to interface with the MLJ toolbox, and MLJ provides the rest, whatever the rest means. Okay. Then you have ScientificTypes.jl. It's quite an important but very lightweight bit of the universe, and it doesn't have to be in MLJ. Actually, you could use it even in a completely independent way. So I'll talk about this. Then there is MLJModels, which gathers a bunch of interfaces to existing packages, so that right now, if you start with MLJ, you will be able to load things from sklearn or from decisiontree.jl or etc. In the long term, we'd like the content of that repository up to a certain extent to be offloaded to package maintainers and not to us, so that MLJModels doesn't grow like crazy, and then we have to manage to sort of maintain a very complicated code with interfaces with a number of packages, right? And then we have to deal with versions, etc., which would be difficult. But let's say it's there now so that you can make use of MLJ directly. Then there are 2 sort of more experimental repositories. One is MLJFlux, which aims to be an interface to Flux from MLJ. To allow to call Flux from MLJ, yeah. And then MLJLinearModels, so I wrote that, and it will be publicly announced soon, I guess. But it's effectively generalized linear models, and it's different. Okay, so if you're familiar with the ecosystem in Julia, then you might be aware of GLM.jl, which already does some linear models. This MLJLinearModels, it does more what sklearn does, in that you can do logistic regression with penalties, things like elastic net or quantile regression or least absolute deviation regression. So all of that now is in one package, and some bits and pieces again were here and there in the ML community, in the Julia ML community. A large chunk of it unmaintained, and so now that's there and it will be maintained in the future. And finally, that's also a very new addition to the universe. We've started, we're well aware that people who have tried MLJ were a little bit baffled because there is not much in terms of sort of getting started with the code, right? So now MLJ Tutorials is both a repository of example and a website that I'll show at the end, which just showcases some tutorials that you can follow and over time we'll add end-to-end examples there as well so that you can just see how things are done, right? Okay, so a short warning is most of the things are, I think it should be clear that even though we've worked on this for, well, I think Anthony's been working on this for a year and a half now. I mean, some of the stuff are still in flux, right, are still being discussed, but most of what we'll discuss today is pretty set. But if you're interested in some of the finer details, some of the finer design decision, just some of them are still up for discussion if you really don't like a choice or another. But you'll have to convince us of that. So, okay, and then so for core design question, Anthony is usually the best person to ask. So I'm probably a good person to ask if you want to interface with MLJ, or if you just have general questions on how to do ML things in MLJ. But for specific design questions, why did we do machines, like you'll see in a minute, just ask Anthony. And we'll open a GitHub. I think Sebastian may have already done that. There is a GitHub issue on the main repositories on MLJ.jl where you can ask further questions. So we'll add like a FAQ style issue and we'll chip in. So whatever I can't answer today, we'll make sure that someone answers it in the near future. Right, so I told you one of the repositories was ScientificTypes.jl. And it's a very lightweight package which just aims to help define how to interpret data. So maybe I can give a very quick motivation for this. If you just load data, and for instance, your data has MF, 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 and NA, for instance, right? If you just load that somewhere, you kind of you may want there to be an automatic interpretation that this is a multi-class variable, right? Like that you have the class M, the class F, and maybe like another third NA class, either missing or whatever. But so there is the idea that this is decoupled from the way the data is currently encoded, which is a string or a vector of strings. Okay, so that's what ScientificTypes does. That's it. Right? So it helps us declare how the data should be interpreted by you and also by the models that you're going to call. So it distinguishes between a machine type, which is like how the data is encoded right now. For instance, it typically will be just a bare bone Julia type, like float64 or a char or whatever. And the scientific type is sort of vanilla, syntactic sugar around this, on how it should be interpreted. So I'll show in a minute the tree of type, but basically you have continuous, multi-class, etc. So that's the type hierarchy for scientific types. So you have either known or unknown. Unknown is you don't know what, like MLJ doesn't, well, MLJ or anything else that calls scientific type won't know what that specific variable is. Usually you don't want that. So in the known type, you'll have either finite or infinite. And in the finite, you have multi-class or ordered factor. So ordered factor, for instance, if you have reviews, right, with like 1, 2, 3, then the idea that 3 is larger than 1. Whereas multi-class, there is no ordering. And then in infinite, whether it's a continuous value or a count. So it might, you might think that there can be a one-to-one relationship between the two, right? For instance, if you get given a floating point value, I don't know, 3.14, it might seem natural to just automatically go to continuous. And that would be encoded in a so-called convention. Okay? So a convention defines a basic mapping or a basic guess, given a data type, given a machine type, what should be the scientific type. But of course, so for instance, the MLJ convention, which is the only convention that's present at the moment, but you could define other ones, it maps an abstract flow to continuous, which is, I guess, what would be the intuition. But such conventions are necessarily a little bit vague, right? So for instance, it could be that you've got like a 3.14, but actually in that column, you only have two distinct values, 3.14 and 5.2. So even though they're encoded as a floating point number, you would want maybe to consider them as a multi-class, okay? And so to do that, to specify explicitly how things should be interpreted, you can use the coerce method. So for instance, here you can coerce an arbitrary table X to have its column age to be interpreted as continuous. Okay. And of course, this could be cumbersome if you have lots of columns. So there is this auto type which does the same thing, but you can specify rules on how to do this. So for instance, actually this is one of the default rules that you can use. The few to finite rule would just take any column that has relatively few values and just map them to multi-class or ordered vector. Okay. That's the idea, at least it's the idea behind the scientific type. So you load the data, and then once it's loaded, you have this interpretation layer. How should it be considered by whatever comes after? Okay. So now that scientific types is out of the way, let's cover the core. So as I said, I'll just bundle MLJ and MLJBase in just one functionality just to simplify things. So an MLJ model is just a container for hyperparameters. And that's it. It just contains hyperparameters. So just to give a small example, for instance, a KNN classifier would only contain the K, right? So specify the K in the nearest neighbors. Well, that's not a good example because there is no other parameter. But okay, so if you take a linear regression, for instance, the only hyperparameter may be whether you're going to fit the intercept or not. Okay, so that's like a Boolean. But the vector of coefficients that you would fit, that will not be contained in that model. Okay? Right. So the subtypes of models, as could have been expected, there is either supervised or unsupervised. So supervised is everything all the rules you want to learn, and unsupervised all the data transformations. And in supervised, we distinguish between probabilistic and deterministic models. So that again, if you've used sklearn before, this should come as reasonably natural. But the split between probabilistic and deterministic is done a little bit. It's a bit stronger. And so the support for probabilistic models is much richer in MLJ than in quite a lot of other packages. And so it uses, if you have a probabilistic model, effectively it will return objects of like the distributions.jl package. So distribution.jl, for those who wouldn't know, is a very nice package that defines a ton load of distributions. And so whatever the output of a probabilistic model, it will be a distribution. Okay. Yeah.
Supervised probabilistic set is orthogonal to the scientific types.
It's independent, yeah.
Right. So you'd have like a probabilistic model over a continuous variable versus over a categorical variable, and that would be whether you got like discrete or continuous.
Right. Okay. So, okay, maybe this slide will help clarify some of it. So to every model that are available, there is metadata attached to the model that you can query. And for instance, at the very least, there is a target, there is an input type, understood scientific type, and an output type, also scientific type. And so you can query the models that are available to you based on what kind of data they can handle, and also what's their expected target. So if you take, for instance, a probabilistic classifier over categorical values, well, the model would have as input type some input, for instance, continuous, right? Like it can take an array of numbers. And the output, the target, would be a categorical, right? Or like a multi-class. And then on top of that, it would return these distributions object for one for every level. So one score for every level.
One distribution for every level?
No. Sorry. So let's say you're predicting over 5 instances, and it's a binary classification problem. Then you'll get 5 times of effectively a vector of scores, right? So a score for class 0, a score for class 1. Yeah. Make sense? Yeah. Right. So this metadata allows to filter models that are available to you at any one time, and to specify traits of the models you may want to use. So there is a bunch of useful things here. The matching XY. Effectively, you just give data, and it tells you every model that will work on that data. Okay, so for this, it uses the scientific type. And then, for instance, here you might want to say, oh, I just want probabilistic model. Okay, so that's convenient again because potentially there is a large number of models, but you only want the models that will work with your data, and you only want models that have specific properties. Okay, you can also filter, for instance, the license over the license of the package. So if you only want MIT license packages, which in Julia is very common, but not in R, for instance, then again you can do that. Okay. So once you've selected or you've picked your model, you can just you load the model into the namespace, into the project by doing add load. And what, oops, no, that's not what I wanted. So what the add load does is it imports the model, but usually this model is provided by a package, so it also loads that package, right? So in this case, for instance, it comes from nearest neighbors, so it will load that package and then make K-NN classifier available. By the way, you don't have to specify the package equals something, but you will have to specify it if it's ambiguous. So already with the number of models we have just right now, for instance, linear regressor is offered by 3 packages, right? So you'd want to specify whether it's going to be multivariate stats, or whether it's going to be scikit-learn or some other. By the way, I should say that everything all the code examples that are presented are on the website, this MLJ tutorials, which I'll show you at the end. So whatever, like if you want to redo some of this, I'll also put the slides online, but all of these codes are sort of worked through in the MLJ tutorials. Okay, so once you've loaded the model, this is the kind of things you'll see. And so that's a model. So it's a struct around a bunch of hyperparameters. So here you recognize K, of course, and then a number of other things. Okay. And now I told you that a model only wraps the hyperparameters, so we need to specify where the fitted results will be, and that's what a machine is for. So a machine wraps a model and the data that it's supposed to be trained on. Okay, so to do this, you just use the keyword machine, and then the model and the data. Right. Oh, this is annoying. I apologize. I'll stop clicking on the screen. Okay, so once a machine has been trained, you can use it as a mathematical operation. So you can use it to predict or transform any compatible data. Right now, it's a box or a function, if you will, and any data that meets the specifications from X here, so the same site type, you can use it to predict Right, so to see this step by step, for instance, you could specify a train and test split. So that's just a bunch of row indices, right? So this partition each index, that's not specific to sklearn, but if each index will return an iterator, 1 to the number of elements, and then the partition will just take the first 70 after having shuffled it, right? So you could just get a bunch of row indices for the train and the test set. You don't specify that in the machine. So in the machine, you just say you will draw your data from that spot, okay? But when you fit it, you say, I only want you to fit on the rows that correspond to this, right? To like the training rows. Is that clear? So the machine wraps around the full data, and then when you fit, you specify which specific data you want. To predict should come as no surprise. You use your machine, and you specify the rows that you want. So you can either specify the rows, or here actually you could predict on new data, of course. So you could pass, instead of rows equals test, you could just pass data that meets the specifications. Right. Same for unsupervised models. So for instance, here in this, if you want to standardize your data, you wrap a machine around the standardizer, which does what you think it does, and the data, and then you just transform your data calling the machine, okay? Right, so the only difference with that from maybe other frameworks is that everything is wrapped in a machine, but apart from that, the rest should be pretty natural. Yes, yeah.
Hold on a minute, Lyndon. Sorry, can you use a mic? Otherwise, the recording won't get it.
Sorry, could you clarify why I have to pass in twice? So if I look at the last, the standardized example, first I gave the machine X, and then I called transform and I gave it to X again.
Yeah.
Is this to do with it finding out the types or something?
Right. So for now, and to simplify things, the only reason why it appears twice is that on the first step, it's the fit or the training of the method. And on the second step, you could apply it on any data, and we happen to have to apply it on the same data, right? So I think what you're hinting at is that we might want to write some syntactic sugar for this to implicitly just, when you do transform stand, it just does it on the data that the machine is wrapped around. This may happen. Okay. Okay, so to tune hyperparameters, oh, sorry, I apologize, sorry. Yes. Okay, actually, it's easy. It's exactly the same. There is no difference, right? The only difference is that the preds here, instead of being values, will be scores, okay? For probabilistic models as well, what you have on top of that is you have, so this predict will return a vector of scores. But you also have available to you a predict mode, which will return the majority class, okay? That answers your question, yeah. Right, so hyperparameter tuning. Hyperparameter tuning, again, like it's sort of baked in the design that we'd want to not only have easy hyperparameter tuning, but also that it's reasonably easy for nested models, right? Like we talked about composability, and of course we want to do hyperparameter tuning of composed models. So effectively, it always works around this range function. And the range function takes a model, so like the bear cane, and I wrote bear to distinguish between a model and the machine that would wrap the model, okay? So whenever I write bear or something like KNN model, it means just the model, not the machine, okay? And then I need to specify which of its hyperparameters I'm going to tune. So here, K. I did what I said I wouldn't do. Maybe if I do this. Yeah, okay, whatever. Okay, so, and now K is a numerical value. So you just have to specify a range of values, actually, when's the name, right? A range of values for which you will do the hyperparameter tuning. So here you just need to specify a lower bound and an upper bound for that range. For a non-numerical value, you would specify the values explicitly. So I'll show an example for this. Just to go over every instance, the bare model is a model instance. It should be : k here is a reference to one of the hyperparameters, so in this case, k. And then lower and upper specify a range of values. For non-numeric, you would write the same thing, except that you would specify the values explicitly. Right now, there is no lower up or upper. You would specify the range of values. So for instance, KD tree or bool tree for the algorithm. So once you have a range, then you need to specify how you're going to sample hyperparameter values from that range, and then how you're going to evaluate over these possible hyperparameters. So that's what a tuned model does. So a tuned model, it wraps around a bare model. It takes ranges for hyperparameters. You could have any number of ranges here. It takes a measure for how it should prefer models with specific tuples of hyperparameters. And then you could add some other stuff specifying how you're going to do the sampling. Okay, so if you don't specify it, it just does a grid search, right? So you could specify tuning. Here, implicitly, it's a grid search. And resampling, so implicitly, it's a cross-validation resampling. Okay. Again, there are more worked through examples if you want on the website. I'm just trying to give an idea of how things sort of generally work. Okay. And then how do you train this tuned model? Well, it's the same as tuning just a model. So you wrap it in a machine with the data, and then you call fit on it. Okay. Right. So now the thing that MLJ is actually good for, or that goes beyond what you would find somewhere else, and it's model composition. So first I need to quickly go over ensembles, and I think I only have one slide for that. So you can do just ensembling, like bagging, for instance, by calling this ensemble model and then specifying what the atom is, so whatever model you're going to repeat over, how many times you're going to repeat. So here 20, so you get 20 KNNs. You put the whole thing in a machine, and then you use this evaluate. So by the way, you can use evaluate for other models as well. So I'm just showing this here. And what this will do is it will do a cross-validation of your data, and then it will just test the model on all of those folds. Okay. So well, I'll skip this because. So more interestingly, or maybe more importantly, are pipelines and learning networks. Pipelines is when you want easy composition, and learning networks is when you want more complicated learning networks. So whenever you can't do something with pipelines, you should try learning networks. That's the gist. So pipelines just allow you, it's a little bit similar, again, if you come from an sklearn background, it's a bit similar to pipeline in sklearn. You just specify a sequence of steps, okay? The difference with the learning network is that in a pipeline, the sequence is linear, whereas in a learning network, you could have branching operations. Right. So for a pipeline, there is this convenient add pipeline macro. And effectively, a pipeline, it defines a new model, a new nested model, in fact. So when you write p equals add pipeline, blah, 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 what it does is it defines a new model, model ABC in this case. You specify the steps that correspond to that model. So here, the first step would be to remember there is this coerce step that you can do to specify how the data should be interpreted. So here it starts with this, and then you do one-hot encoding on all of your categorical features, and then you would apply, for instance, a KNN regression. And you can specify how the target should be transformed as well. So for instance, here, you would want to do a standardization of the target. By the way, this might seem silly, but there is an open issue, again, on sklearn since 2015 on how to do this last bit, right? The target equals univariate standardized. So at the moment, as far as I'm aware, you can't specify how the target will be transformed. You're going to have to do it a priori and then train your pipeline on the data and the pre-standardized output. Cool, and then so that's a new model with nested hyperparameters, which you can access with the dot syntax. So p.knn to get the knn step, and then .k because it's a hyperparameter of that step. And consequently, the hyperparameter tuning will happen in the same way. You just have to specify the nesting, but otherwise it's the same. So it's the same as before. You have this range, but now instead of just saying k, you say that it's k from knn. So you just need to specify that nesting. The rest is the same. So specify a lower bound, an upper bound. You can specify the scale, and that will. So if you don't specify it, it will be a linear grid between the lower and the upper bound. If you specify it, it will be, for instance, in this case, it will go by like a logarithmic grid. Any questions on pipelines? Yeah.
In the pipeline, so when you do the tune model, is only the tuning of the model repeated, or every step of the pipeline is repeated for every range value?
So I want to check that I understood the question first. So I understand the question as being is
has several steps. So
yes.
One hot encode, the queries and so on, and then you pass that P to tune model.
Yeah.
Right? So when you do the range, does he every time he tries a different set of parameters, does he repeat every step of the pipeline, or does he only evaluate?
Okay. So I guess the question is, if you have a nested model and you try to tune the hyperparameters, does it retune what it does? What does it retrain what kind of has been trained before, and it doesn't need to in a way? So for instance, if you're modifying k, am I going in the right direction? If you're trying to modify k, are you going to redo the one-hot encoding as many times as you're going to fit k? Well, the answer is no. So there is. We'll talk about nodes in a minute. But every operation can be considered as a node in a graph, and whatever node is considered up to date will not be retrained, right? So for instance, the one-hot encoding would not be retrained. However, if you modify things and then downstream of that operation, it depends upon that node, then that will be retrained, but it needs to. Okay, so a learning network is just a pipeline on steroids in a way. So you define a graph of operations from the data that you input all the way to the output. Everything is a node, so a node can be understood as operations. And it starts from the source node, and then you flow through operations, which can either be mathematical operations like take the log of this, or like concatenate these vectors, or can be models, trained models, or like machines, right? So fit can be called at any point of, that defines a directed acyclic graph. And you can fit at any point of the graph. Of course, you'll probably want to fit at the end so that it fits the whole thing, but you could want to explore at intermediate steps, and you can do that. And it will just, MLJ will just train whatever is upstream of the node you're trying to fit, okay? So I'll do, this is a small example, but okay, I'll show two things here. One is the sort of the expanded syntax of how to define such a learning network on a simple example. And then there is a much more compressed syntax for this. And then, yeah, well, so let's go. You start with defining the source nodes. So this is where you the input data. And you have to specify which one is your target. And then you would specify your operations in order. So for instance, you want to transform the data and you want to standardize it. You want to transform the output and you want to do like a box-Cox transformation, doesn't matter. And now that you have these two steps, you want to feed that into a ridge regression. So you could see this as layers, right? So at the first layer, you standardize the data and you do the box-Cox transformation. On the second layer, you have this ridge regression, which takes the output of the first layer. And then on the last layer, you need to inverse the initial transformation that was done on the target, right? So that you can output something that's comparable to the input data. Okay? So that defines the graph, and then so up to this last line, nothing has been trained, and then when you call fit, it trains whatever it needs to train. If you've done some, if you've queried the model before, for instance, at some point you've trained the box model just to check that it was doing what it should be doing. When you later on call the overall fit, it won't retrain that node. Okay, exactly as you said. Right, and so with Julia, the 1.3 version, there is some neat tricks which allow us to write a much shorter syntax. Effectively, everything becomes callable. Everything becomes a function, and so you can use what we'll refer to as for want of better names, the arrow syntax. Now, if you're not familiar with Julia, this just means call the function on the right on the data on the left, right? So if you said like, if you had a function square and you had 2 arrows square, it would be 4. So this is just syntactic sugar to say standardizer of X, right? But it's better, it's kind of nicer to write it this way because it kind of indicates what you're doing, like, or the flow of operations. So you get this secondary node W from X by just going through a standardizer. You get this secondary node Z from Y by going through this box-Cox transform. Then you concatenate the two and you send them through a ridge regression. And finally, you inverse the transform. So that's identical to the previous one, but of course much shorter. So it's kind of nicer. Right. And to tune a learning network, I think I'll kind of skim over this, but tuning a learning network is done in much the same way as before. You just have to define a model around your learning network once you're happy with it. And then once you have a model, you do the hyperparameter tuning, much as we've done hyperparameter tuning before. Okay. Okay. So that kind of, ideally, well, hopefully maybe that shows you a little bit of what MLJ does and how it does things. If you give it a shot now, there's quite a bunch of models that are already available from nearest neighbors, so like KNN, classification, regression. There's decision tree, random forest. There is clustering, GPs, and then a bunch of linear models. There's pretty much most of the sklearn's classifiers and regressors, including ensemble models, by the way. And so all of this is kind of interfaced in MLJ models. So if you're interested in knowing what models are available right now, you can either call the model function from Julia and it will give you a full list, or you can go to that repository where you will find the same full list. Okay. Yeah. And so more models will come as well. So I mentioned these sort of fancy generalized linear models. This will be added hopefully within the next 2 weeks. And there is something I kind of forgot to mention. I'm sorry, I should have mentioned this in the vision. We're very much hoping to interact with the probabilistic programming community in Julia. And so this, again, it should happen over the next week or so. So we've had some very interesting conversations with the guy, one of the developer, well, the main developer from SOS, and also people who work on Turing.jl to try to see how to make the interfaces compatible. And it looks like SOS is quite promising, and hopefully in some future, I think Turing.jl is doing some pretty huge amount of refactoring, or has been recently. And so they first wanted to get that sorted out before talking to us. But so hopefully probabilistic programming will become a thing as well with MLJ, which would be great. Okay, so where are we going in a few slides? So in the short term, we want to experiment, get user feedback, finalize the design, and sort of promote interfacing with MLJ. So if people have MySuperModel.jl that they can easily interface with us, and so we'll help people do that. So if you happen to be such a person, or you know such a person, please get in touch. And so we'll add end-to-end tutorials as well. In the middle term, there is something that I did not touch upon at all, but MLJ aims to have sort of to facilitate systematic benchmarking of a range of models. If you train a bunch of models and you want to know which one is really the best one, beyond this sort of just doing cross-validation on a single model. So this could be quite nice, and do that for a range of metrics as well, not just one. Advanced hyperparameter tuning, so there is a whole team over there working on how to do things beyond sort of grid search, etc. And hopefully we'll pull that into MLJ at some point. So that would be really cool. And then probabilistic programming, as I mentioned. And in the long term, there is sort of what I hinted at very early on, that if we express these composed models as a directed acyclic graph, can we exploit parallelism? Can we things like scheduling? Because often in ML, what's nice is that on a given node, on a simple node, you kind of know what's happening on that node. You know how much time it's going to take because you know how much computational effort will go into it. So that would potentially allow to write like a scheduler for how things should happen, and benefit from if you have multiple processors available to you, can you like train your model faster, etc. So I mean these things, the last few things, it's all up in the air. And so if you're keen and you want to help, you can help us in many ways. And so I've listed a few here with some indication of how much machine learning and how much Julia you should know to help. So if you have some experience with machine learning and not so much with Julia, you can already help by just testing MLJ. So just load data and then try to apply models, and give us feedback on what you found counterintuitive or what worked well, or just help us write more tutorials, suggest features. That would be great, especially in the short term, to help more users sort of benefit from end-to-end examples. If you're a bit better, if you're a bit more familiar with Julia, you can help us interface with more packages. So this is already happening. We've already got contributions from people trying to help us interface with more of this the Julia ML ecosystem. That's really great. So if you want to help, get in touch. Probably get in touch with me. If you're very good at Julia, and it doesn't matter how good in ML you are, there's probably a lot of things that can be improved in the code base. We try to pay attention to how things are done, but at the moment our focus has been to really provide like a nice design for machine learning, and sometimes at the expense of, let's say, specifying the types properly or whatever. So if you're interested in using Julia for and sort of optimize Julia, we're interested, definitely. And then if you're an ML expert and you have some Julia knowledge, then there is a lot of stuff we can discuss. So how to add more hyperparameter tuning strategies beyond the ones that we have now. how to integrate with probabilistic programming, how to do the scheduling I mentioned before, etc. Right. Any questions? And I'll show us.
For questions, can you please use the mic? Otherwise, the recording folks are not very happy for obvious reasons.
Yeah, I don't know if you're aware. Is that okay? Yeah. I don't know if you're aware that today in Python 3.8, the Walrus Operator was introduced, which is the assignment operator. As a Pascal programmer, I would say becomes equal to. So for the arrow operator, I think we should call it the Grumpy Cat Operator. Maybe. We need an animal for it, definitely.
All right, sounds good. Actually, I think this Walrus Operator is pretty cool, but yeah.
Good. Yes.
Thanks, very nice talk. When you train when you train the model on the training data, does it store, for instance, the indices you've trained on somewhere in the model? So, for instance, if the user were to save, I think it was called a machine, wasn't it? If the user were to save that machine and then reload it, is there any way for them to tell what indices the data was trained on?
I don't think so.
Because that could be a useful thing, right? Because you've got the data's already in the machine, so the indices each index should always return the same thing. So it may improve portability if you could.
So I think generally in terms of sort of saving models, like serializing models and things, I mean, it's probably not been a thing that we've looked at a lot. So there is probably things like low-hanging fruits that can be done there. So if you have suggestions on how to do this, don't hesitate in opening issues. I think it's a good point.
A serious answer to your question, actually, to Joe's question is, the company I work for uses Kubernetes exclusively, and obviously that machine could be a Kubernetes container. We use a framework called Polyaxon, if anyone has heard of it, Poliaxon. And I think that can do that job of storing those parameters in that fashion. So an interface between this and Polyaxon might be actually very interesting and might work very well. Maybe worth looking up.
Thanks. Any other questions?
Yeah.
Sorry.
I was just wondering, like long term, it seems like you guys are almost swelling a bit, or is that true with the package?
You mean in terms of the number of repositories? Or?
Yeah, and stuff like that. Like, where do you see yourself in the Julia kind of ecosystem? Like, there seems to be quite a few different kind of, I don't know, families of stuff.
Okay, so I think the key bits are the first three packages, so ScientificTypes, MLJ, and MLJModels. Sorry, ScientificType, MLJ, and MLJBase. That's not really going to change.
Yeah.
There may be a number of other auxiliary packages that implement specific interfaces to specific stuff, but it's not really the core. The core is MLJ and MLJBase.
Yeah.
And that's not going to change. I think ScientificTypes was taken out of these two because people just thought, like, I think Anthony had a discussion with one of the maintainer for low-rank models.jl, and it turned out that, or I think actually you suggested that.
And they say as well, like ScientificTypes is a fantastic idea, and like everyone should just get on board and use that for like all kinds of things, like graphing. Can use it to decide, do I want to display this type of graph or that kind of graph?
Right. So ScientificTypes is going to stay outside of the thing. It's kind of independent. We use it, but it's independent. And but yeah, so I think it will remain MLJ and MLJBase, the two core packages. What goes in each of the two, that might be fine-tuned over time. But I think it's pretty close to what we want now. So I don't think there will be, I hope there won't be many more packages added to that, because there is a fine dance on Git to try to sort of synchronize everything when we do releases, etc. So that's like our penalty. We're self-regularizing the number of repositories. Yeah.
Okay. Thank you.
And so how do we see ourselves in the Julia community? I think we just very much hope to have a positive influence in terms of making people use more the models that are there, and through usage, sort of encouraging package developers to just maintain their package or improve performances or whatever.
Yeah.
So I think if that can be achieved, that would already be a pretty positive, I think, for Julia.
Yeah. I think it's a very good like kind of modularity that you guys got going. So I think
Yeah, cool. And after this, I have a short demo as well, right? So yeah, there will be more more time for questions afterwards, depending on when you have to get back.
Yeah, I'm someone new to Julia and sort of data science. I'm just curious, when you do development with, for example, this library, do you do it in a Jupyter notebook with like a Julia extension, or you just do it with the normal files and you run it with a compiler?
Right.
So if I want to try out your library, which approach would you recommend?
So I mean, if you really like Jupyter notebooks, you can do that. I personally don't use them. I use Juno. So that's it's like a Julia editor hosted in Atom, right? I think it does everything I want, so I can try code quickly in the console, and then I can modify the code directly. Actually, I do everything in Juno. So if you're new to Julia and you have no strong opinion as to what you should be using, I would recommend you try that. I think there is a similar version in VS Code, but I think Juno is more feature-rich. At this latter point, I'm not sure. I've never
Can
used
we
VS Code.
hold questions till after the demo? Let's just get to the demo and then
Cool.
we'll
Thanks.
come back for questions.
Right.
That'll be a better use of time, I think. So off you go.
I was a little bit worried for 2 seconds. Okay, so by the way, this is the website, MLJ tutorials. So there is a repository and the generated website. So on that website, at the moment, there is not a ton of stuff, but there should be enough to get you started. So everything that I said is in those few first getting started points. And this is, so each page is effectively a script, right? So you can download the scripts and then run them by yourself, or you can download a notebook and run them by yourself. And the end-to-end examples, I think we'll try to grow that quite a bit. At the moment, there is only 2 toy models, one with XGBoost. I'll show you those in a second. So yeah, just go to the website to get started if you're interested. Right. So let's... Okay, I'll show a small example with XGBoost. So in this example, we load in both this and the other example, which I'll hopefully show as well. We load some really simple data, and this one particularly simple. So the crabs data set is just 200 crabs with like a category that you care about. And you just predict it. Using XGBoost is completely overkill for this, but it doesn't matter. It's just a simple use case where we can show the parameter tuning, and the parameter tuning is very fast because the data is very small, right? Okay, so it looks like this. So you have the features here. This is your input matrix. By the way, note that everything is in float, and the guessed scientific type is continuous everywhere, which is fine, so we don't have to coerce anything. You can check the levels of Y, so the classes of Y, so that's just B and O here. So it's going to be a binary classification problem. We split the training and test, so that's the magic line I had showed you before. Just partition the indices into a 70-30 split. You can specify a random number generator to make things more reproducible. So even though I think it would still be nice to be able to save the indices, if you specify the random number generator, you can reproduce your experiment. You load the model using the add load macro, and then you define this bare bones XGB model, so which is just the container for the hyperparameter. So you can have a look at the hyperparameter. So it has a large number of of hyperparameters, and we will try to tune some of them. Okay. So you can check whether the data is balanced. In this case, it's actually almost perfectly balanced. If you did this count map of y, of the full targeted, I think there is perfectly 100, 100. So it's really a bit of a toy example, but that's fine. So now that's the usual procedure which I talked about in the talk. So you define the bare bones model. We've already done this, but okay. Then we wrap it in data. So you call this machine of the bare bones model x and y. And then we want to start tune it. So let's first tune the number of rounds, so the number of trees you're going to grow for the XG boost. So you specify a range with the lower and upper, and the hyperparameter is num round. Here it's not nested, so you can just directly specify the hyperparameter. And we didn't talk about what the learning curve is, but it does exactly what you think it does. So it will do cross-validation and evaluate over each of the folds, and then you can just draw the curve for the number of things. I won't get into the specifics, but the only interesting point is the measure here. We specify that what we care about is the cross entropy. So that's actually the default measure for classification. And the resolution indicates how many points in the range you're going to draw, so between 10 and 500. So by the way, in all of the hyperparameter tuning in MLJ, you always specify hyperparameters, numeric hyperparameters through this range function between lower and upper, and then you specify a resolution, right? We will also soon add the possibility to sample from it at random according to a distribution, but that's not there yet. Okay. So you can plot this, and it will look like this, right? For the learning curve, it's a bit big, but if I decrease it. And so, out of just looking at this, you could retrieve this from the measurements, but it's nicer to see it in a curve. You can say that anywhere around 100 rounds is fine, and then it sort of plateaus. So you can fix it to 100. And again, you can access hyperparameters through this dot syntax. So just xgb dot the hyperparameter in question and specify, so fix it to 100 from now on. Okay, so now that we've fixed the number of rounds, we can also try to tune jointly, tune things jointly. You could do more than 2, but if you do 2, you can have nice 2D visualization, which is the purpose of this. So for instance, we could try to optimize or to tune over the maximum depth of each tree, or the child weight. Again, same story, you specify a lower and upper. And now, actually, there is this tuned model, which we've seen before, but this time we specify explicitly the grid. So that's going to be a grid search, a standard grid search. And the resolution indicates, well, how coarse the grid is. So in this case, we have 2 hyperparameters, and we specify a grid with resolution 8. So there will be 64 pairs of hyperparameters we'll train over. Use cross-validation, specify a random number generator for reproducibility again. Specify the ranges, and then you fit all that. And again, you can show this as a nice sort of heat map where it becomes reasonably clear that this area is more promising. So like 5, 1.4 or something. So again, we can fix this. And then you could do more tuning. I mean, I'll stop here because you're bored already. But so you could do this tuning, this exploratory tuning, fairly easily. Once you've done the tuning, you can explore what the best parameters are by using these fitted params that you can call on any machine, and that will just return whatever it has like whatever the training has returned, right? So in this particular case, you can extract the best model, which is quite convenient. But if you were to use these fitted params, let's say on a trained linear regression, you could recover the coefficients of the linear regression. Okay, I think probably I could mention more details, but inevitably it becomes a bit of an information overload with all of the functions that you can call. I think the key here is to just get a sort of rough idea for how things are running. Right, I won't do the last one, but you can run through this in your own time with explanations, etc. By just going to the website and downloading the notebook, or just running it, or just reading through it, and give us feedback on it. Right. Okay. Thanks.